Hi everyone, and welcome to Advanced Insights. I'm Mark Papermaster, CTO and EVP at AMD. I'm excited to continue this series where we provide just what the show name suggests, advanced insights into some of the most exciting trends and topics in technology. Now's a quick intro. Amin is an engineering fellow and VP and GM for machine learning, systems, and cloud AI at Google. He is an ACM fellow and a member of the National Academy of Engineering. In the past, he was the SAIC Professor of Computer Science and Engineering at UC San Diego. Amin, I have been so looking forward to this conversation because after of course, we've had the opportunity to work together, and you've been such a great customer, such a great partner. But I didn't know the side of you that really, steps back and studied the industry. And when I read your blog, and this was after your most recent keynote, University of Washington, about the 5 epochs of distributed computing, it absolutely hit home for me because I grew up in those areas. I started with, IBM decades ago, right in that first epoch. And it has truly just been amazing what the industry has gone through. And I just feel like that you captured it so well. And particularly the impact that distributed computing has had on the way that we all live and work and play. So thank you for joining us here today.
It's my real pleasure, Mark. Pleasure to have the opportunity to speak with you. You and I have had the chance to work together for quite some time now. We've partnered on some, what for me has been really gratifying collaborations together, taking to market some great products around AMD products and many more in the future. So really been looking forward to this, but also your career has been quite distinguished. I know, as you said, we were talking about this beforehand, you started your career in 1982. So you've seen so much of this history and actually I think contributed tremendously to so much of this history. But it is, for me, really fascinating to reflect back on just how far we've come in really a short amount of time. I mean, I started, at least you could start arbitrarily far back, but I started in about 1970 in looking at the history. And so really 54 years, that's a tiny amount of time. And thinking about how much the world and technology has changed in that period is really, really incredible, awe-inspiring, and also humbling.
No, it is. And what I love that you flagged is that it's not incremental innovations, it's leapfrog innovations, and that's how you determine the epochs. And of course, it started with PCs and telnetting to get that very basic infrastructure, and then the impact of the web and of mobile computing, and then really getting our first real distributed systems and clusters, and think about the first big high performance compute. Those there's only the likes of national labs that could build that kind of distributed computing, and now they're a fraction of the size of what you run at Google.
To me, this point in 1970 was a really amazing time. And I think back to what it must have been like and the possibilities and people really inventing really almost on a blank canvas. But if we consider some of the, I think, true breakthrough inventions that took place around this time period, this is all within about a 5-year period where we had things like the C programming language, the Unix operating system, the Intel 4004, which was really the first microprocessor. We had graphical user interfaces, object-oriented programming, laser printing, really database systems, relational databases, all invented at approximately the same time as this other little invention called the internet. Right? The first 4 nodes of the internet actually came up in 1969. And all of these things today continue to be the underpinnings of modern computing. Now, of course, they've come, just as you said, tremendous distance in the intervening 50 years, but somehow built on, of course, decades of previous work and advancements, many things came together simultaneously to really be the underpinnings of modern computing still today. Ethernet. We didn't capture Ethernet, which of course now connects billions of devices really in the end across the planet.
Well, you think about those innovations and the kind of the impact they've had. You know, you've personally been involved in so many of them, and you know, I think about what you've done to allow, you know, clustering beyond and expansion. So, you know, for those that don't follow it closely, the only way that you know we can keep computing at a Moore's law pace. Moore's law was a doubling of transistor density, but we all relied on it to really double every 18 months our computing capabilities. And we all know, everyone knows that that's slowed. And so it is the ability to take advantage of course, multi-cores, but to scale them with networking capabilities and create, again, the kind of clusters you have today. I mean, before we get to the fifth epoch of computing, if you could just give me a little perspective of where we're at today. I mean, the kind of challenges you've tackled over the last few years in creating true scale-out capability to meet both your internal Google needs with all the computing that those customers use, and then Google Cloud.
Yeah, it's been, of course, as we've discussed, an incredible journey. I mean, starting, we'll talk about some of the work that you did for just a second, and you were really at the forefront of. So starting in 1970, when we really had supercomputers, and in fact, the internet was perhaps one of the primary drivers for the internet, was to allow humans, people, to have remote access to supercomputers. Right? You logged into them. You ran the file transfer protocol to move your data back and forth. You ran simulations and experiments because they were these giant, expensive computers of which you could only afford a tiny number, like single numbers across an entire country. Of course, humans were spread across the country, so you needed a network to connect these supercomputing centers essentially to one another and to people. But thanks to Moore's law and the incredible exponential progress that was made year over year, those same supercomputers became actually the size of a desktop. Right? And hence, around 1982, maybe it was exactly 1982, the IBM PC was born. And there were personal computers before that, but now this device that you could imagine putting on every desktop, every worker's desktop at home, etc. So really the power of computing came to everyday people. It wasn't something that you had to now log into remotely. And then from there, of course, technologies like Ethernet allowed these computers to connect to one another, heralding client-server computing, heralding true distributed computation. Right? You now had file systems that you could share among many computers. But throughout this entire period, individual computers were becoming more and more powerful. Right? And in other words, as you wanted to run bigger workloads, you took advantage of Moore's law. And you took advantage of the next generation of maybe 18 months later that was twice as fast. Right, twice as capable, maybe had twice as much memory, twice as much hard drive storage, all for the same cost. So every 18 months or so, every 24 months or so, you doubled your capability. You do that a few times, 5, 8, 10 times, right? 10 doublings is a factor of 1,000. So pretty soon you now have the capability for the same cost to do much, much more than you ever imagined possible. Now, as you said, somewhere around the year 2000, plus or minus, this doubling in performance for the same power started to slow or stop. What that meant was that we couldn't make, and you're very, very familiar with this, and you've continued to, of course, with your tremendous work at AMD, drive progress despite this challenge, substantial progress despite this challenge. You couldn't make individual CPUs, individual cores, twice as fast every, let's say, 18 or 24 months. You could add more of them. And this then led to the notion of not scale up computing, but scale out. You had to go with parallelism. And this then naturally led to cluster-based computing. And really, whether it was Google, whether it was many contemporaneous companies at the same time, including, of course, research and academia, the notion of cluster-based computing took root. And now we could imagine delivering planetary scale computing by essentially deploying a large number of commodity servers, running commodity open source operating systems. So the notion of scaling up to the next biggest computer stopped, but the notion of scaling out at tremendous scale really took a hold. And now, when you needed more computing power, you didn't wait for the next model necessarily. You bought more of those. You scaled out horizontally. And of course, then how do you organize things? because programming these things, managing these things becomes radically different. The abstraction of a single computer is really powerful. Right? In other words, it's much easier to program one computer with your task than to program 100, 1,000, 10,000. Today, perhaps 100,000 or more computers might be involved in a single request to a web service. How do you coordinate all that? So really, the algorithms, the software, the control systems, all have had to evolve tremendously. Let's say in these time periods since about 2000 where cluster-based computing took hold.
I mean, it's so amazing to me. So you think about what you just walked us through, what led up to these 2000s, and think about the confluence, because that created a scale up and a scale out capability that aligned with the ability to use accelerators to marry that with algorithms of artificial intelligence and machine learning that is now having a profound impact on society as a whole. And to me, it's just amazing how that confluence has come together and what that portends. I mean, it's actually underlying your premise of Epic 5, of where we find ourselves today.
Yeah, and so to me, this has been one of the most incredible things is that over the past, let's say, 10, 15 years, we've really gotten to a place where we can take for granted having access to the totality, the really totality of human knowledge at your fingertips instantaneously in a device the size of a cell phone. Right? In your palm, you now have more computing power, much more computing power than the largest supercomputers of the 70s and 80s. And through that, on a very high-speed network connection, you have access to essentially every song ever recorded, every movie ever made, and of course, all your favorite encyclopedia articles, research articles, and more. So the availability of this data, this digital store of human knowledge, along with tremendous amounts of compute, initially general-purpose compute, more recently accelerators, which I know we'll talk about shortly, allowed us to actually build a new class of algorithms that has led to some of the breakthroughs in artificial intelligence that we're seeing today. Right, this incredible amount of data, incredible amount of compute can come together to really organize information in ways never imagined before.
You mentioned, in the blog you wrote, that it's an insatiable demand for more computing, and I love that phrase. I use the same phrase, and it ties in exactly to what you said. Is now going forward in this era, this epoch, it's going to take just immense innovation on every front. I use a phrase I call holistic design, of that we're going to need every element. We're going to need, yes, Moore's law is slow, but we need new semiconductor nodes at every turn that give us the best device performance, give us more energy efficiency. We need to package that in ever more innovative ways. At AMD, we've leaned in on a modular approach and a chiplet approach, and many in the industry are also using this approach. But it goes on to the whole stack of buildup to the clusters you described, and I grew up where it was a hardware-first world. Now it's really a software-first world. Software-defined networking, software-defined storage, and software-driven build-out to get the scalability that you described. So I'd love to get your thoughts on what you said. It's going to take new types of accelerators. I know internally, with your deep knowledge of the algorithms, you're developing silicon at Google, and as our other hyperscalers, we're not going to slow down in the industry. Those like AMD and others, as we provide more general purpose and ASIC capabilities. Would love to get your thoughts on that insatiable capacity, and what does that mean for the industry and sort of this new order of multiple points of innovation of silicon and systems.
Yeah, so just as we thought we were getting on top of the problem of really, really challenging classic problem of web search and information retrieval, we had a new problem statement for us, which was, what would it mean if all of Google's users were to interact with Google services via voice for 30 seconds a day? Just 30 seconds a day of voice interaction for each one of our users. And we realized that if we were to build out our infrastructure in the way that we'd traditionally done, it would mean, and this was 10 years ago, a little bit more than 10 years ago actually now, that we had this thought experiment. We realized that supporting this one use case would require building 10 Googles, basically 10x more capacity than we had available to us. And we realized that, the traditional ways, and we thought, hey, scale-out computing, cluster-based computing, software-defined networking, software-defined storage, we thought we had a good handle on many of the right design patterns, but we didn't know how to handle the seemingly simple problem of voice interaction. We realized that we had to build a different kind of computer. It turned out to be a tensor processing unit, or TPU, for the sole purpose of performing inference, such that we could efficiently run the job of turning human voice into, computer bits, text in the end, that we could run through our algorithms. And this was the first generation of TPUs. Second generation of TPUs, and led to third, led to fourth. We're now on our fifth generation of TPUs for both serving and training. Around 2017, researchers at Google, in Google Research, had a breakthrough in a fundamental new modeling technique for deep learning called transformers that allows us to, again, organize huge amounts of information and serve it unsupervised. So now we could take, essentially, again, this totality of human knowledge and train on it and be able to serve it at scale. But again, the compute costs, right? Insatiable is absolutely right to do so, both for the training and serving costs, was enormous. We're seeing that these models, I've shared this with you before, and it really is incredible. Over the past 6 years, year over year, the size of these models has grown by a factor of 10 every year. And the compute costs are at least linear, meaning at least proportional, if not more than proportional, with the size of the models. That's a fact, right? 10 to the 6, again, these things multiply up rather quickly, is a factor of 1 million. We talked about the power of Moore's law. I've never seen anything like this. I think, Mark, you would agree. We've never seen anything like this. This rate
Yes.
of growth and demand for compute, just unbelievable, which then says we have to do things differently. Like, to even have a hope of keeping up, we have to do things differently.
And so, when you look at how the industry is going to attack this, you're going to continue to develop, approaches that, really require that deep, innate knowledge of the application, like you just described, that drove the TPU development. We're gonna continue general purpose. What is your view that one type of acceleration will win all and the others go away, or is the size of the tent large enough to accommodate multiple computing approaches going forward?
Yeah, this is a really great question, and one that I think about a lot. I know you and I have had a chance to discuss this one, Mark. In the heyday of Moore's law, when computers were really doubling in performance capability every 18, 24 months for the same cost, specialized accelerators typically didn't stand a chance. Right? They took too long to develop. They maybe didn't have a big enough advantage to keep up with that onslaught of Moore's law's capabilities. But also, they typically also went after a smaller portion. Like, in other words, if you could make 5% of your workload twice as fast, well, you're going to lose to Moore's law. If you can make 5% of your workload 10 times as fast, well, you're probably still going to lose to Moore's law because the wins aren't big enough. In this machine learning training world, though, as I talked about, 90% of our workload on general purpose compute might have been for this machine learning workload. So now it made sense to try to accelerate, especially when Moore's law in terms of raw performance improvements wasn't delivering the same benefits. Looking forward, I do see more accelerators emerging. General purpose compute will continue to have a deep and important role. We're doing a huge amount, as you know, of general purpose compute in our infrastructure. I see that continuing for the foreseeable future. But I do think that there are a number of other workloads that really bear out for acceleration. One that we're already doing, and we have collaborations underway with you and others, is, of course, security and encryption. Again, this is a well-understood workload, mathematically intense, and one that lends itself to acceleration quite well. So I think this is going to continue. Video processing is another one that I think lends itself nicely to acceleration. An emerging one that a number of us are quite excited about is data analytics and processing. Right? This is also a huge fraction of our workloads, many companies and customers' workloads. So I think this is another place where there is good opportunity for acceleration. But then I think the other nice thing that yourself, Mark, and others, but certainly AMD has really been at the forefront is now we're seeing different flavors of general purpose compute. In other words, it's not just one CPU chip that you sell for 18 or 24 months. You might actually have, within the same family, of course, all perhaps x86, etc. You're going to have variations that might hit different points in the, let's say, memory bandwidth to CPU performance ratios, or maybe maximum performance per core relative to the total number of cores. Just picking some examples that may or may not be pursued, of course. And different workloads can then be mapped, and you can think of it as a form of accelerator to different variants of the general purpose compute as well.
I think people don't realize just what you stated. I'm going to emphasize it. It used to be, if you looked at a data center 10 years ago, it was a homogeneous computing approach. It was primarily one processor type, x86 processor, and a lot of that was done for all the reasons you stated, and it simplified that optimization point, a single optimization point. But if we did that today and didn't have the benefit of those tailored processors, whether it be different forms of CPU, tailored CPU computing, the accelerators, GPUs, specialized chips like TPU, we would not achieve the efficiencies to address those insatiable demands in computing. And I'm going to pivot to one correlate with it. If we didn't have that type of specialized computing, how are we going to attack the challenge that we face in the industry of power?
Thanks for raising this, Mark. It's something that is near and dear to my heart, and I think for Google overall. As you know, Google has a commitment that by 2030 we get to net zero carbon footprint 24/7. Well, what this means is not zero carbon via offset, but zero emissions across our entire planetary infrastructure. This is a bold and extremely challenging goal, one that we're deeply committed to. But what it really then says is we've historically been focused on a measure, what we've thought to be, and it's a pretty good measure, a holistic measure of how we evaluate our infrastructure and how we map workloads to our hardware infrastructure. And we refer to that as perf over the total cost of ownership. Performance captures our workload characteristics. Think of it as a benchmark suite. Total cost of ownership captures the cost of acquiring our infrastructure, our servers, our racks, memory, CPUs, of course, storage, and more. But it also accounts for power, both the power provisioned to place them in a data center building, but then the power draw of actually powering that infrastructure and running it. Google has been at the forefront of such efficiency work. We introduced the metric probably coming up on about 20 years ago now called PUE, the power utilization efficiency.
Yeah, we all use it now. It's an industry standard measurement.
Exactly. And this is essentially saying that for how many watts of power do you have to provision to a building to be able to deliver 1 watt to a server? In other words, how efficient is that delivery of power for running compute? And actually, when we started, industry standard was somewhere between 2.5 and 3. In other words, you had to provision 2.5 to 3 watts of power to deliver 1 watt to a server to do work. Pretty inefficient. We're now to a place now where Google, depending on the location, can hit 1.1, and others as well, not just us. But really, this is the basis for saying, you know what? A key metric for us and for the industry is this power utilization efficiency. Today, we're seeing an expansion of this where we're extremely focused on performance normalized to just power, not performance necessarily for total cost of ownership, because we see that power is the precious commodity. So we want to be able to deliver the best delivered performance per watt globally. And this then drives our optimizations across the board, also accounting for, of course, where power is available, where net zero carbon offset power is available, et cetera, over the course of the day, the week, depending on workloads and more. And I think that, of course, energy efficiency, I know, is top of mind for you and the AMD team, and you build some of the most energy efficient CPUs there are, and thank you for that. Certainly our customers and ourselves internally benefit from it. But I think there's much more work to be done in ensuring that we continue to remain vigilant of the importance and the limitations of power in delivering all this computational capacity.
I think all of us appreciate the focus you've had on energy efficiency, and absolutely it's fundamental at AMD. And what I think is important, you mentioned like the work you all did at Google on PUE, and you've been involved in many other things that have become standards. There's work that may have started at Google and it may be a different approach that one of your competitors did, but you've been active and open to come together on standards that would actually help the whole industry in areas where, for instance, Parthon, your team's been a leader in open compute, and I'll look at an example of security where we were able to partner with yourselves, Microsoft. Now many others are coming in, so we established a common way across the industry of root of trust. Now in networking, there's standards opportunities to work together. It's so competitive what you're doing at Google, and so you're constantly balancing, what you need to keep proprietary and where it does in fact make sense that the industry needs to move together.
Yeah, this has been a journey for us, and again, really appreciate the partnership in security, networking, compute, and so much more. For us, we've been on a push, and I've been supportive of a push to being increasingly open, and in fact, open first. So, for example, our work in Google Cloud, we consider ourselves and we advocate for it as the open cloud. So, in other words, we've really gotten to a place where we want to be open first. And we want to lead and ideally win when appropriate based on having the best technology, not necessarily based on lock-in or proprietary technology. So wherever we can, where actually it helps customers and users having a standard set of well-vetted techniques. Security, I think, is a great example. In other words, we really think that everyone wins from having trusted, vetted, openly verified security protocols and security hardware. Right? This is something that is very easy to get wrong. Right? And just the smallest, tiniest oversight can lead to exploits and attacks. So all of us benefit from working together because no one wins from a security exploit or a security hole. So working together with yourselves and others on things like this only makes all of our infrastructure stronger. And this infrastructure is, again, as we were talking about beforehand, Mark, increasingly critical to society. In fact, I often refer to it as societal infrastructure. And so ensuring that the things that are just foundational to the operation of that infrastructure is open, has the best minds on it, is verified, is secure, is just absolutely so important to us.
It creates having an immutable trust is essential when you think about the growth of AI applications. How much of critical infrastructure is going to be dependent on computing, but computing that you can trust. And so what a perfect example of where we need to continue to come together as an industry. What I love is partnering with competitors where we really need standards to come together. It's been so impactful.
That's right. I think that we should be, of course, raising the bar collectively across industry on the efficiency, on the capability of our infrastructure. But for the table stakes, we must be working together for the highest levels of reliability, for security, and more.
So I'd love to hit on a topic that's near and dear to me. I've been, had the opportunity to be in the industry for decades, and I've worked with such great people. And if I look back on that, I'd say, that culture has been sort of an enduring factor of how teams can really accomplish. If you have the right culture, they come together, they innovate, they get great things out, and frankly, with the bad culture, the converse happens. I know that's near and dear to you as well, Amin. How do you think about culture? You run a massive team. How do you even communicate your thoughts on that factor to your development engineers?
Yeah, absolutely. And culture is 100% central. And so for me, I think about the ingredients that I value. And I mean, this is something I know you've learned, I've learned over the years, is the team absolutely emulates what they see the leadership is doing and what they see leadership talking about. And for me, culture starts with respect. Respecting one another, basically treating each other with the highest level of respect. That's one place where it starts. I hope to be able to show that and emulate that. But I think as much is one of growth mindset. And this is something, again, I think about for myself, and this is something that I discuss with my team regularly. In other words, I would say early on in my career, early on in my life, how often did I catch myself applying static mindset and static thinking to others? oh, this is how this person is. They can never get any better. I'll let others be the judge, but I think I'm much, much better than I was 5 or 10 years ago. And way, way better than I was 15 or 20 years ago. So I'm willing to give myself the benefit of the doubt for growth. Most of us, all of us, are set on improving. So A, do you have that growth mindset for yourself? I think that's where it starts. Do you believe that you can get better? You will get better. Now let's take it to the next level. Am I going to help them get better? Is that part of my job? Is to raise up those around me. And the final bit is this growth mindset and static mindset with respect to groups and teams. As you said, some of us are privileged to have large organizations. I see what I sometimes refer to as village mentality set in, which is to say, you know, my village is the best village in the world. That village, you know, mile down the road, not a very good village. They don't do things well. In fact, they seem to be a little bit slower than us. They seem to be a little bit less smart than us. Our village is the best. And the further you go, the less smart and less kind and less nice the people of those villages seem to be. This to me is poison. I mean, and for me, I really remind my teams, and I try to live this with certainly my partner teams and my peers, partners across industry, partners within the company. These are all incredible people. They're committed to doing the right thing. They're committed to growth, and very, very likely they're just as capable as you are. They're just as committed as you are. And if you start with that, actually, rather than start with, oh well, they're in a different village, they speak a different language, right? They have different priorities, they have evil intent. None of this works out. None of this ends well. So I think that these, to me, are some of the elements of culture that are so important. And then in terms of communicating it, the best way I know is to live it, speak it, and do your best as much as you can to set that example.
I mean, those are great leadership insights that you shared with us. And I see it. I see it working with you. I work with so many of your different teams. And frankly, as I said, culture is very big to us at AMD. And I think it's been actually the underpinnings of what we've been able to do together. And so it's really so much appreciated. I'm sure not just by AMD, but all the other companies and partners that you have in the industry. With that, I mean, I want to really just give my immense thanks for you joining us here today. What a great discussion, and just your thoughtful insights of where we've been and where we're going. I am jazzed looking at the future.
It's been a real pleasure, Mark, and I have to say that I've been doing this for a while. You've been doing it for even longer. We both have the privilege of some perspective, but I have to say that even across all this time, all these epochs that we've experienced, I actually have not been in a more exciting moment in the computing industry than this moment. I mean this with all sincerity. In other words, what's in the air with respect to what's possible and what will be is just absolutely astounding. And what we're going to be doing together across industry to realize the possible over the coming years, I just can't wait. It's going to be tremendous.
We've got our running shoes on. We're ready to sprint with you. It's going to be an incredible race. Amin, thank you again.
My pleasure. Thank you for having me, Mark. I love this conversation. Thank you.
I truly enjoyed my discussion with Amin. Thank you for joining us today on Advanced Insights. I look forward to bringing you more in-depth conversations on cutting-edge technology, industry insights, and visionary perspectives from some of the brightest minds in the field. If you enjoyed today's discussion, don't forget to subscribe to AMD on YouTube and follow me on LinkedIn so that you never miss a future episode. Technology is always advancing, and I can't wait to share more insights with you next time.